Let's continue our talk on the air standard cycle. Last time we talked about the Otto cycle, and we have proved the thermal efficiency relation for the air standard Otto cycle, which is function of the compression ratio R and also function of the specific heat ratio K. And we have seen last time, Shabab, that this efficiency, thermal efficiency, increase as the compression ratio increase. But we said last time this air standard Otto cycle can be applied for gasoline engine, but there is a limitation for the compression ratio in gasoline engine due to the engine locking. So we cannot increase the compression ratio in a gasoline engine more than almost 11 compression ratio, so that we can limit the maximum temperature and maximum pressure within the cycle to the safe limit to avoid engine lock. And we said we can increase this efficiency, still it is function of the specific heat ratio. We said if we replace the air, the case of air, the specific heat is 1.4. But if we use another working fluid like monoatomic, any monoatomic actually gas like argon, helium, all of these gases have a specific heat ratio higher than the specific heat ratio for air, and that may result actually in a higher, and it will result for sure for a higher thermal efficiency for gasoline engine. And I told you also last time, one of the current research work is going on the argon power cycle, in which we use a mixture of argon plus oxygen as oxidizer instead of air to raise the specific heat ratio and to raise actually the thermal efficiency. This engine, Shabab, in order to just recycle the argon back from the cycle, it should be actually use the hydrogen as a fuel, or in some cases it can still use also hydrocarbon fuel. But the idea here, Shabab, of argon power cycle, which is still under current research, is to use a gas that has higher specific heat ratios than air, then we can raise the thermal efficiency of the gasoline engine. Inshallah, today we'll be talking about the air standard diesel cycle, which can be applied actually to the diesel engine. But for the diesel engine, Shabab, we have two cycles. One cycle, which we call it the diesel cycle, which can be applied actually to the early version of the compression ignition engine, or we can say this can be applied to the ideal engine. And we have the modified cycle for the diesel engine, which we call it the dual cycle. Dual cycle, inshallah, we'll be talking about it next time, which applied for the modern compression ignition engine. So what is the difference between early compression ignition engine and the modern compression ignition engine? Anyone have idea, Shabab? The old version compression ignition diesel engine and the modern version, what is the difference? Anyone have idea? So it's okay. So for the early compression ignition engine, Shabab, they used to have the injection when the piston at the top dead center by the end of the compression stroke. And in this case, the combustion process will take place during the expansion stroke. So once we start the combustion, the pressure inside the cylinder will try to raise, but the piston is moving down in the expansion stroke, so the pressure will try to reduce down. So we have one parameter, which is combustion, will try to raise the pressure. Another parameter, which is the expansion of the piston, will try to reduce the pressure. And at the end, during the combustion process, we can approximate, as you can see here in the left-hand side figure, the combustion process almost at constant pressure at the beginning of the expansion stroke. Then after the combustion, the piston will continue in the expansion process. And on the other hand, for the modern diesel engine, they decide actually to inject the fuel early before the top dead center. So that means the combustion will take place before the top dead center. And in this case, we can have instantaneous combustion when the piston is at the top dead center, like the case of gasoline engine. Part of the combustion will take place at constant volume when the piston is just at the top dead center. And then the remaining part of the combustion process will take place at constant pressure during the expansion stroke. And in this case, Shabab, for the modern compression ignition engine, in which we have the combustion, part of it take place at constant volume and the other part take place at constant pressure, we call this cycle, Shabab, as the dual cycle. Inshallah, we'll be talking about it next time. But today, inshallah, I'll be talking about the diesel cycle, which applied actually for early version of the compression ignition engine, or we call it the ideal compression ignition engine, in which all of the combustion process take place during the expansion process under constant pressure, during the first part of the expansion process and under constant pressure in this case. And in this case, the fuel is injected just at the top dead center, not before the top dead center. Here is the actual cycle for the diesel engine. We have fuel, we have air is coming in during the intake stroke while the piston moving down. Then we can compress this air. At the end of the compression stroke at the top dead center, we will start injecting the fuel, and then the fuel will start igniting during the expansion stroke. At the end, we will have also the exhaust stroke. But for, as I told you, for all of the air standard diesel, or all of the air standard cycle, including Otto cycle, diesel cycle, dual cycle, all of this cycle, we consider the system is closed. So we don't have intake valve or exhaust valve. Just the working fluid is air. We don't have fuel. All processes are reversible. We don't have combustion. We don't have exhaust. Just we have heat addition and heat rejection in this case. But what is different here, Shabab, in air standard diesel cycle, that the heat is added under constant pressure during the expansion stroke. In case of Otto cycle, this heat addition process was added under constant volume. Type, let's look at this cycle, the air standard diesel cycle, and look at the different processes, and try also to develop a relation how to calculate the thermal efficiency of the diesel engine based on the diesel cycle. Is that clear, Shabab? Is it clear?
Yes.
So I will be talking about the air standard diesel cycle. So let's define all of the processes for this cycle and try to calculate the thermal efficiency of this cycle. If you look at the diesel cycle, Shabab, on the PV diagram, the representation on the PV diagram. So if this line representing the top dead center and that line representing the volume inside the cylinder at the bottom dead center. If we started this cycle as usual, by the end of the compression, by the end of the suction stroke or the intake stroke, at the bottom when the piston is at the bottom dead center, so the piston will be moving up from the bottom dead center to the top dead center for process from 1 to 2. During this process, we should have actually apply work on the piston. So the work is coming in this case from the crankshaft to move the piston upward. So in this case, we have what's called the compression work. And this process from 1 to 2, we said we don't have friction. All processes are reversible. So we don't have also heat transfer. So adiabatic and reversible process, that means this process from 1 to 2 is an isentropic process. So process from 1 to 2 is isentropic compression process. Isentropic compression, that means you have the entropy is constant, or in this case, the change of entropy from the initial state 1 to the final state 2 is equal to 0. Type, we said isentropic is an adiabatic process. So in this case, the heat transfer is equal to 0. And the process actually is a reversible process. And in this case, we should apply work. This work is the compression work, should be applied on the piston. And in this case, this work, Shabab, should have a negative sign. We said for a closed system, work is equal to integration of BdV. In this case, delta V from 1 to 2 will equal to V2 minus V1, which should be negative in this case. So this term is negative. That means this work in this case will be negative. And as we said last time, Shabab, for any process on the PV diagram, the area under the curve on the PV diagram is representing the work. So the compression work in this case can be represented by the area on the PV diagram under the process from 1 to 2. Okay. So the second process at point number 2, when the piston reaches the top dead center, fuel will start to be injected. And in this case, the combustion will start. But as I told you, when you start the combustion process, heat will be added, so the pressure will try to raise up. But the piston is moving down toward the bottom dead center, so it will try to reduce the pressure. And at the end, this heat addition process will be added under constant pressure in this case, from process from 2 to 3. So the process from 2 to 3 is constant pressure. Pressure is equal to constant heat addition process. So in this case, heat should be added in this case. But is there work, Shabab, during this process from 2 to 3? Is there work, or the work in this case is 0?
0.
Are you sure, Shabab?
Oh, no.
There should be work, because in this case, شباب, we said work on the VV diagram is the area under the curve. So from 2 to 3, we have constant pressure process. If the pressure is constant, work is equal to integration of VDV. That means the work pressure is constant will equal to pressure integration of delta V will equal to V3 minus V2. So this is the work during the combustion process. Because the pressure is the process, in this case heat addition is under constant pressure. If it is constant volume here, شباب, just a vertical line like the Otto cycle, so the area under this vertical line will be 0. And in this case, delta V will be 0. So work while the heat addition under the constant volume process will be 0 in this case. But in this case, the work, the heat is added under constant pressure. So we have area under the curve and we have exchange delta V. Pressure is constant, the integration of delta V will equal to V3 minus V2. So the work during the combustion process will equal to the pressure multiplied by the difference in volume, which is V3 minus V2. The third process, شباب, which will continue after the combustion process, the piston is continue moving down for the process from 3 to 4, in which we can get the expansion or the power of the engine. So the process from 3 to 4 is isentropic expansion process. Isentropic expansion, that means delta S is equal to 0. The process is isentropic, so the heat transfer in this case is equal to 0. But during this power stroke from 3 to 4, in this case we can get a positive work, which is the power output of the engine that should be produced during the expansion stroke from 3 to 4. Once we reach point 4 here, so the exhaust valve, in the case of real engine, will start opening. Once the valve opens, some gases will directly be left, actually leaving the engine under constant volume when the piston is at the bottom dead center, due to actually the difference in pressure between the pressure at this point and the atmospheric pressure. So the gases will be just leaving very fast in this case, while the piston is at the bottom dead center. This process, we can call it as the heat rejection process under constant volume. But still the piston is at the bottom dead center. So as I told you, in case of all of the air standard cycle, we don't consider intake or exhaust valve. But if we can just approximate this cycle to be applied for the diesel engine, in this case at point 1, when we reach actually point 1 back, and the piston is at the bottom dead center, in this case the piston will be moving upward toward the top dead center to have the exhaust stroke under constant pressure. And then at the same line, we can reverse the process. Piston will be moving down from the top dead center to the bottom dead center during the intake stroke. But this line, as I told you last time, we have to exclude from the air standard cycle, because in the air standard cycle, we don't consider intake or exhaust valve. In this case, شباب, we just consider we have a certain amount of air in a piston cylinder device, and we add heat and reject heat. We don't have any intake or exhaust valve. But this is a representation of the diesel engine at the end. But let's look at all of these processes and try to develop a relation how we can calculate the thermal efficiency for a diesel engine based on the diesel cycle, which is an ideal cycle. But as we said, this should give us indication about the limit of the efficiency of the diesel engine. But let's consider process by process, like what we have done in the case of Otto cycle, and try to get a relation for the thermal efficiency in this case. But let's consider process from 1 to 2, which is the isentropic compression process. Isentropic, that means, as we said, delta S should equal to 0. And in this case, the heat transfer, the system should be adiabatic and reversible, so we don't have heat transfer in this case. For all processes, we assume for all air standard cycle that we have a closed system. The system is closed with constant specific heat. Cv is constant and Cv is constant, are not function of temperature. Or we can say K, which is the specific heat ratio, is constant. But for a closed system, if I apply the first law of thermodynamics, it will be Q minus what will equal to delta U, which is the total exchange of internal energy, which is equal to mass multiplied by the difference in a specific internal energy. This is the total internal energy in kilojoule. This is the mass in kilogram, and this is the specific internal energy in kilojoule per kilogram. Usually, شباب, in tables, if you look at the thermodynamic tables, usually you will find the value of the specific internal energies that are listed in the table. You will not find the total internal energy. But if we divide by the mass, both sides, so we can say, first of all, heat transfer in this process is 0. So we can say the specific work, W small, which is the total work divided by mass, will equal to the specific internal energy U2 minus U1. And for the ideal gas, we are following here the ideal gas model. So the work will equal to the change of delta U, which is CV for ideal gas multiplied by T2 minus T1. In this case, شباب, this work from 1 to 2 is equal to integration of BdV. Delta V in this case, which is V2 minus V1, is negative. And as we said, this work is a compression work because this work is not produced by the piston. In this case, the piston during the compression stroke, it takes power from the crankshaft. So that should be a consumed work, which is a compression work. So it should be of negative sign. So negative with negative sign will be positive here. And that should equal to U2 minus U1 for the ideal gas. Delta U is equal to CV multiplied by delta V. And this is what we call the compression work during the compression process. And this process is isentropic. We have proved last time that for an isentropic process, we can say T2 over T1 will be the same as B2 over B1 to the power K minus 1 over K. And it is the same as V1 over V2 to the power K in this case. And the V1 over V2 is equal to what? This volume V1 minus V2 is the displacement volume between the top dead center and the bottom dead center. And this volume, when the piston is at the top dead center, should be the clearance volume in this case. And that means the volume at point 1 will equal to the displacement volume plus the clearance volume, which is the total cylinder volume. And the volume at point 2, which is the clearance, that means V1 over V2 is equal to the compression ratio, and that should be raised to the power K in this case. And this relation is very important. If I told you we have a air standard diesel cycle, and I want to calculate if, let's say, I have the properties at the intake manifold at the end of the intake stroke at point 1, give you pressure, temperature at point 1. Then in this case, I will ask you to calculate the pressure and temperature at point 2. Then we can use this relation. If I ask you to calculate the compression work, or if you need to calculate the compression work, then in this case we can say it will equal to CV multiplied by delta T. Is that clear, Shabab? Is it clear?
Yes.
Let's move to the process, second process from 2 to 3. So as you know, Shabab, the course is coordinated with another section. The programme is given. So the exam, maybe we may have some common question, yani. And also because we don't have the same chapters, and the sequence of chapters are also different, but we should have some common exam, some common problem in the midterm exam. And also will take almost this chapter will be included in the midterm. So please try to follow this chapter. We don't have sheet, homework to solve for this chapter, but I think it should be there in your midterm. Okay, let's consider the second process, which is the heat addition process from 2 to 3. So in this case, we have heat is added, okay, and we said this is a constant pressure process, so we should have a work in this case. But this process, Shabab, the pressure is constant, so V2 is the same as B3. Let's apply the first law of thermodynamics for a closed system. It will be Q minus work equal to delta U, or equal to mass multiplied by change of a specific energy. If we divide by mass, it will be Q minus work will equal to delta U, which is CV multiplied by T3 minus T. Let's leave it first, U3 minus U2. Okay, This is U3 minus U2. But what about this work, ya شباب? If we have a closed system, ya شباب, here, this is a closed system. Let's say we have a gas in a piston cylinder device. And this piston is just fixed here. If we add it heat here, ya شباب, so it will be the volume will be constant. Because the piston is not moving. So what will happen to the pressure inside here? Pressure will be what? Mustafa?
It will increase.
So the pressure for sure will be increased in this case. But if we allow this piston to move, and I add it heat, it is free to move. If I add it heat, so the gas, the pressure will try to increase, but the gas will try to expand. And this piston will allow for this expansion. So what will happen to the pressure in this case?
It will be constant.
Exactly, so the pressure in this case will be remaining constant. But part of this heat, ya شباب, will be used in what? Will be used to move to move this piston. We call it actually a boundary work in this case. So the only way for a closed system to have a constant pressure process is through the movement of one of the boundary. Because if all boundaries are not moving and we have a closed system, the pressure will rise. So the only way to have a constant pressure process for a closed system is through the movement of the boundary in this case. And this will result actually in a boundary work. So part of this heat will be consumed to move the boundary. And in this case, we call it the boundary work, which is equal to integration of PdV. If the pressure remained constant, so that will be pressure, integration of delta V, which will equal to V3 minus V2 in this case. So the work in this process, شباب, is a boundary work, while the heat addition process from 2 to 3, we should have boundary work. This boundary work under constant pressure will equal to pressure multiplied by V3 minus V2. So let's substitute here. Then we can say the heat transfer. Let's take this work to the other side. It will equal to the pressure, which is constant. V3 is the same as V2. So let's say V3 minus V2, plus we have U3, we have here U3 minus U2. Okay, by V3 plus U3, this is the enthalpy H at H3, and we have U2, V2, this is the enthalpy actually H2. So that means the heat transfer in this case, heat transfer, will equal to the difference in enthalpy H3 minus H2. And for an ideal gas, delta H is equal to Cv delta T, so that should equal to the specific heat at constant pressure, Cv multiplied by T3 minus T2. And this is the heat added during the constant pressure combustion process, should equal to the difference in enthalpy, will equal to Cv, the specific heat at constant pressure for the working fluid, which is air, which is equal to the specific heat for air multiplied by T3 minus T2. But this process is constant pressure. So V3 is the same as V2. If we apply the ideal gas relation, we can say V3 over T3 is equal to V2 divided by T2. But we have the same pressure. V2 is the same as V3. So that means T3 over T2 will be the same as V3. T3 over T2 will be the same as V3 divided by V2. And the ratio between the volume after the combustion process, which is V3, divided by the volume before the compression process, which is V2, we call it the cutoff ratio. We call it RC. So RC is defined as the cutoff ratio, which represents the ratio of the volume. It is defined as the ratio of the volume after the combustion process divided by the volume before the combustion process. We call it RC, which is the cutoff ratio in this case. Okay, this is a very important parameter, Shabab, because we will derive the efficiency of a diesel engine as function of this cutoff ratio. So the cutoff ratio is the ratio of the volume inside the cylinder after and before the combustion process. But process from 3 to 4, This is the isentropic expansion process from 3 to 4. So we can apply the relation similar to the process from 1 to 2, but in this case we have positive work in this case. So the process from 3 to 4, which is we have isentropic expansion, which we have delta S should equal to 0 and the heat transfer should equal to 0. I think we should have an idea about this maybe somewhere. Don't know if all of you have this idea. But anyway, so let's prove it. So Q minus 4 will equal to the same delta U, which is U4 minus U3. So we don't have heat transfer. The process is adiabatic as it is isentropic. And we have the work in this case is positive, but we have negative sign here. So that means the work, which is the expansion work, will equal to U3 minus U4, which will equal to CV multiplied by T3 minus T4. And this is the expansion work. And the expansion work is isentropic process. So we can say T4 over T3, we can apply the isentropic relation, will equal to V4 over V3 to the power K minus 1 over K, will equal to V3 over V4 to the power K. Okay? If we consider this term, it should have V3 over V4 as V3 over V2 multiplied by V2 divided by V4. All of this to the power K. So V3 over V2, we have represented this term as the cutoff ratio RC. And we have V2 over V4, which is actually the ratio between the clearance volume to the cylinder volume. So this ratio is equal to 1 over the compression ratio. So we can say this term will equal to the compression, the cutoff ratio RC divided by the compression ratio R to the power K. Okay? And this is the ratio of the isentropic relation T4 over T3 is B4 over B3 to the power K minus 1 over K equal to V3 over V4 to the power K. You can divide it V3 over V2 multiplied by V2 over V4. V3 over V2 is the cutoff ratio and the V2 over V4 is one of the compression ratio, and that should equal to RC over R to the power all to the power K in this case. Okay, Shabab? Is it clear, Shabab? Is it clear, Hussam? Sam, is it clear?
Yes.
Okay. Right, let's move forward with the last process, and then we can prove actually the thermal efficiency for a diesel cycle. So the last process, which is the process. Sorry. Which is the heat rejection process. We have heat is rejected in this case, but the process is constant volume. So the process from 4 to 1, this is constant volume process. So the value of the work in this case will equal to what, from 4 to 1?
0.
It will equal to 0 because the work is equal to, for a closed system, VdV. And we have delta V is 0 because the volume is constant. So the work in this case will equal to 0. If we apply the first law of thermodynamics, Q minus work is equal to delta U. We don't have work and we have heat rejected. So the heat rejected in this case will equal to, this heat shabab is rejected. So its sign should be what? Should be negative. In the first law of thermodynamics, we have to substitute the heat transfer and the work with this sign. So that should be negative sign. So this delta U is U1 minus U4. From 4 to 1, it will equal to U1 minus U4. But we have negative sign, so it will equal to U4 minus U1, which will equal to CV multiplied by T4 minus T1. And this is the value of the heat rejected in this case, under constant volume for the process from 4 to 1. Type, we said if a system is working on a cycle, the concept of working on a cycle is starting from one point, do whatever the processes you do, and you have to get back to the same point. And in case of a system working on a cycle, that means we have proved last time based on the first law of thermodynamics that Q net, the net heat transfer, should equal to the net work out of this system. Net heat transfer, we can consider the specific value divided by mass. So we can say Q added minus Q rejected will equal to the expansion work, which is the work out, minus the input work, which is the compression work in this case. Also, we have defined the thermal efficiency. Eta thermal for any cycle should equal to the net work divided by Q added. So let's apply this thermal efficiency and try to calculate the thermal efficiency for this cycle. This is the heat rejected. So the thermal efficiency, Eta thermal, will equal to work net work. If we divide by mass, so up and down, it will be the specific value. So it will be small w, work net, which is the work per unit mass, divided by Q added. We are considering, for all of this cycle, closed system. Closed system, that means the mass is constant. Mass is not changing from state 1 to 2 to 3 to 4. All cases we have mass is constant. So we can divide here by mass in this case. We can consider the specific value. That should equal to Q net, work net, which is the same as Q net, based on the cycle, divided by Q added. That should equal to Q net, which is Q added minus Q rejected divided by Q added. That should equal to 1 minus Q rejected divided by Q added. Okay, and we have this term, you can just substitute 1 minus Q rejected, this is the rejected heat, is equal to CV multiplied by T4 minus T1, and we have proved that T added for process from 2 to 3 is equal to delta H, which is CV multiplied by T3 minus T2. And this is how we define the thermal efficiency. This is how we define the thermal efficiency for a diesel engine. But this is in terms of the temperature. So let's try to reduce it down. We need to get it actually as function of the compression ratio, function of the cutoff ratio, and get a more non-dimensionalized relation. Type, this is CB over CV. This term represents what, Shabab?
1 over K.
1 over K, exactly. K is equal to CB over CV. So this term is 1 over K. But we need to make it non-dimensional. So let's take the temperature T1 as a common. So it will be T4 over T1 minus 1 divided by, let's take T2 common. So it will be T2, T3 here over T2 minus 1. Okay? And that should be the thermal efficiency in this case. So what about this term? T4 over T3. For the T4 over T1, we have for process from 3 to 4, which is isentropic expansion, we have proved that T4 over T3 is equal to V3 over V4 to the power K, and we have multiplied by V2 up and down. Then we have reduced this relation just right now equal to R, RC divided by R to the power K minus 1. This is for the isentropic expansion process. We have a relation T4 over T3, but we need T4 divided by T1. But we have for the process from 1 to 2, we have T2 over T1 is equal to V1 over V2 to the power K. This is isentropic compression process. V1 over V2 to the power K, which is the compression ratio R to the power K. Okay? Or we can say T1 over T2 will equal to V2 over V1, which is 1 over R in this case. So we can replace 1, this is R to the power K minus 1, or 1 over R to the power K minus 1. We can replace it by T1 over T2. Then we can say T4 over T3 will equal to RC to the power K divided by R to the power K minus 1. Is it no, not K minus 1, this is K. Okay? RC over R to the power K. So it will be RC to the power K divided by R to the power K, which is T1 divided by T2. So we can replace it by T1 over T2. Okay, and we can take this one. No, this is T1 يا شباب over T2. We have here يا شباب T1 over T2 will equal to 1 over R to the power K minus 1. So 1 over R will equal to T1 over T2. So we can write it actually down this way. Is it clear يا شباب? Is it correct? Let's check together. So T4 over T3 is equal to RC over R to the power K. 1 over R to the power K will equal to T1 over T2. Okay. So that should be correct. So then we can take this to the other side and this one here. Then we can say T4 over T1 will equal to T3 over T2 multiplied by RC, which is the cutoff ratio to the power K. And we have T3 over T2 actually is equal to what? There is something wrong here, Shabab. I have to. So. That is K minus 1, Shabab. Huh? That is K minus 1. K minus 1. Okay. K minus 1. And that should be RC to the power K minus 1. K minus 1. So it will be T4 over T1. Sorry, Shabab. So T4 over T1 will equal to T3 over T2 multiplied RC to the power K minus 1. But T3 over T2 for the constant pressure process from 3 to 2, that should equal to RC, which is the cutoff ratio. So RC multiplied by RC to the power K minus 1. So at the end, this term will equal to RC to the power K. So T4 over T1, this term here, in the thermal efficiency will equal to RC to the power K minus 1. And please try to check it. And we have T3 over T2, this term is equal to RC. And we have T1 over T2, that term is equal to 1 over R to the power K minus 1. If I substituted all of this, then we can come up with the finalized form of the thermal efficiency for a diesel engine. So the thermal efficiency will equal to 1 minus Cv over Cv. We said this is 1 over K. So this is 1 over K multiplied by T1 over T2, which is 1 over R to the power K minus 1. Multiplied by T4 over T3, which is RC to the power K minus 1, divided by T3 over T1 over T2, which is RC minus 1. And this is the thermal efficiency for a diesel engine. Non-dimensional form, which is function of the RC, which is the cutoff ratio, function of R, which is the compression ratio, and also function of the specific heat ratio. So let's write it down this way. So heat thermal will equal to 1 minus 1 over R to the power K minus 1. What does this term represent, Shabab? 1 minus 1 over R to the power K minus 1. That should represent what? The efficiency of the Otto cycle. Here is the efficiency of the Otto cycle. Equal to 1 minus 1 over R to the power K minus 1. But what is added here to this term is this term between bracket RC to the power K minus 1 divided by, let's take this K inside, so K multiplied by RC minus 1. And this is the definition of the thermal efficiency for the diesel engine. If we have this term is equal to 1, so that means in this case the eta thermal for the diesel will equal to eta thermal for what? Eta thermal for Otto cycle. So if this term between bracket is equal to 1, so in this case the efficiency of the diesel engine approaches the efficiency of the gasoline engine. But this is a shabab under the same, if we have the same compression ratio, here you can look at it. This is what we have proved. So here shabab is the relation. If we have the term in bracket is equal to 1, that means the efficiency of the diesel will be approaching the efficiency of the Otto cycle. If we have the same compression ratio, what will be, which engine will have actually the higher efficiency in this case, diesel engine or gasoline engine? For the same compression ratio, R is equal to constant. We have two engines, gasoline engine and diesel engine. Both engines have the same compression ratio. Consider the two engines are working on the air standard cycle. So which one we should have higher efficiency? Diesel or gasoline at the same compression ratio? I think you asked this question before, but now we can answer it theoretically.
Diesel.
Mustafa?
The diesel.
The diesel should be higher efficiency? No, actually for the same compression ratio, the gasoline engine will be of higher efficiency. If you look at this term, usually RC, which is the ratio between the volume V3 over V2, this term RC is greater than 1. And the key for air is equal to 1.4. That means all of this term in between bracket will be greater than 1 for the diesel engine. This term is greater than 1, okay? And we have the efficiency is 1 minus this term multiplied by 1 over R to the power K minus 1. And the case of Otto cycle, this term is equal to 1. In case of gasoline engine, this term is equal to 1. The efficiency is gasoline is equal to 1 minus 1 over R to the power K minus 1. This is the efficiency of gasoline. But in case of diesel, we have to add this term. And this term is greater than 1. That means the thermal efficiency of a diesel engine at the end, all of this term should be less than the case of Otto cycle. Because in case of Otto cycle, this term is equal to 1. The efficiency is defined by this term. But in case of diesel, this term, as RC is greater than 1, that means this term is greater than 1. When we multiply this term, which is greater than 1, by 1 over R to the power K minus 1, and then in this case we have to say 1 minus this term, so the efficiency of the diesel should be less than the efficiency of the gasoline engine at the same compression ratio. So the limiting efficiency for a diesel engine at the same compression ratio is to reach the efficiency of the gasoline engine. But otherwise, shabab, for any other case, without fixing the compression ratio, the diesel engine should result in higher efficiency. Okay, but for the same compression ratio, the diesel engine should have actually lower thermal efficiency in this case. As you can see here, shabab, this is the thermal efficiency for a diesel engine. Typically, the diesel engine are working for compression ratio between 15 and 20. And as you can see here, as we increase the compression ratio, in this case, the thermal efficiency will be increased. So as we increase the compression ratio, R in this term, the thermal efficiency of a diesel engine should be increased in this case. But we say that shabab, in gasoline engine, we have a limitation to increase the compression ratio. Due to what? Due to engine locking. But is there a limitation here as well in the diesel engine to increase the compression ratio? Why we are limited to about 20 or 22 compression ratio? What is the limit in this case? Do anyone have an idea, Shabab? So the limit, Shabab, is the pressure. The compression ratio will give us indication about the pressure at the end of the compression stroke. And this pressure, we have to design the engine, the piston, in order to withstand this high pressure inside the cylinder. And in this case, we have to use more thick material. The material of the engine should be more thick in this case, and it should be heavier in order to withstand this pressure. And in this case, the engine load, the engine weight in this case will be much increased. Increasing the engine weight, that means actually we will need power, engine power, in order to just to carry the engine. Okay, so there will be power loss due to the heavy engine weight. So in this case, we can say there is a limitation on the diesel engine to increase the compression ratio due to the limitation of the material and the weight of the engine. Okay, for a spark ignition engine, Shabab, as we said, if we added more heat in gasoline engine, يعني in gasoline engine يا شباب the processes the heat is added under constant volume. Let's say from 2 to 3 here. If we added more heat, let's say to 3 prime, then the maximum temperature will be raised. This is 3, and this is the expansion process. If I added more heat, then in this case the work also will be increased. We have the efficiency anyway is equal to the net work divided by Qn. Okay? If I raise the heat added in gasoline engine, the efficiency should be reduced. But what happens is that I have raised as well the net work. So in this case, the net work increased, but more than the increase of the heat added. And at the end, actually, the thermal efficiency of a gasoline engine based on the Otto cycle will be increased. In case of diesel engine, if you increases the heat from 2 to 3 under constant pressure, this heat is added during the expansion stroke. So if I add it here, more heat, that means I am cutting off the expansion power, the expansion work in this case. So the expansion work will be reduced in this case. It will be just a small distance, a small pressure difference from 3 to 4. That means if I added more heat in diesel engine, in this case the efficiency will be reduced. The efficiency for the diesel engine will be reduced if I added more heat, unlike the case of gasoline engine, because we add heat here under constant pressure. Okay, but if we reduce the amount of heat added, let's say from instead of 3, let's say 3 prime here, P4.3. That means I have reduced the heat added. Reducing the heat added will result in higher thermal efficiency in this case. But if I am able to reduce the heat added to 0, all of the heat will be added at this point instantaneously. Actually, when the piston is at the top dead center. If heat added is minimum, under constant pressure is equal to 0, that means all of the heat will be added under constant volume, and in this case the efficiency of the diesel engine will be the maximum. And the maximum efficiency for a diesel engine is equal to what, is equal to the efficiency of the Otto cycle of a gasoline engine. At the same, we are talking at the same compression ratio. Okay, so the limiting efficiency for a diesel engine at the same compression ratio is to reach the efficiency of a gasoline engine, which is the efficiency of Otto cycle. Okay, so higher efficiency in case of gasoline engine can be obtained with lower amount of heat added under constant pressure, because heat is added during the expansion stroke, and it cuts the part actually when we add more heat. That means I will reduce the expansion work in this case. Okay, and that's why for a spark ignition engine. So that means, for a diesel engine, the efficiency, the system will be more efficient if we added less amount of heat. That means for the same amount of heat added for gasoline engine and diesel engine, that means the diesel engine will be more efficient in this case. Because the diesel engine, if we added less amount of heat, will result in higher efficiency. But gasoline engine, if I reduce the heat added, the net work will be reduced and the efficiency will be reduced. And that's why for gasoline engine, for the same amount of heat added, heat added is equal to M dot fuel. The heat is added is the fuel energy, M dot fuel multiplied by the heating value. That means the heat added is function of mass flow rate of fuel. So that means if I have the same amount of fuel added for gasoline and diesel engine, the diesel engine should be of higher efficiency in this case. Because as we reduce the heat added in the diesel engine, unlike the case of gasoline, the efficiency in this case will be raised in this case. That means for the same amount of heat added, same amount of fuel, the diesel engine should result actually in higher power in this case. And that's why for gasoline engine, to get the same power like the diesel engine, it has to run at higher speed. And the higher speed, that means actually it has to consume more work in more fuel in this case. Is it clear, Shabab? Is this point clear?
Yes.
Clear, Bad?
Yes, sir. Yes, sir.
Brother, is it clear?
Yes, sir.
طيب, this is the idea, Shabab. If the heat is added in gasoline engine as it is added under constant pressure, if we reduce it, that means the efficiency will be increased in this case. And here it is, Shabab. As you can see, if let's define something before we look at this figure. I will define some dimensionless parameter. Before we can make sure that what we said is correct, that heat added, reducing the heat added under constant pressure in a diesel engine will result in better efficiency in this case. So we have the heat added. If we just develop another relation, heat added is equal to CVM. The total value shall we have to multiply by mass, MCV multiplied by T3 minus T2. Heat added from 3 to 2. That should equal to MCV multiplied by, let's say, T2. We need to get it dimensionless. So it will be T3 over T2. T3 over T2, which is the same as V3 over V2, which is the cutoff ratio, RC, minus 1. And we have T2 over T1. T2 again, T2 over T1 is the same as V1 over V2 to the power K minus 1, which is 1 over R to the power K minus 1. Okay, is it correct? So I can just take T2, so it will be MCV. T2, we can take it T1 multiplied by 1 over R to the power K minus 1 multiplied by RC minus 1. We have here CB is defined as what? CB is defined as K R divided by K minus 1. For an ideal gas, we have defined this relation. CB is equal to KR divided by K minus 1. So that should equal to M KR over K minus 1 multiplied by T1 multiplied by 1 over R to the power K minus 1 multiplied by RC minus 1. Okay? Let's isolate this. So this is the case. We have MRT1, which is B1V1 multiplied by K over K minus 1, 1 over R to the power K minus 1, RC minus 1. And this is the heat added. To make this term dimensionless, I will just divide by B1V1 both sides. So this is B1V1. Now this term is a dimensionless term. It can be applied for any engine. I'm not talking about a specific engine now. This term is dimensionless. That should equal to K over K minus 1, which is the specific heat ratio. 1 over R to the power K minus 1. R is the compression ratio, is a dimensionless parameter multiplied by RC minus 1. And based on this relationship, we can get here. We can get the value of the cutoff ratio as function of this dimensionless parameter, which is Q added divided by V1 V1. And as function also of what of the compression ratio R. So this term, from this relation, I can get the value of RC as function of Q added over V1 V1, which is dimensionless parameter, and also as function of the compression ratio R. And take this and substitute in the term of thermal efficiency is equal to 1 minus 1 over R to the power K minus 1, RC to the power K minus 1 divided by K, RC minus 1. So this thermal efficiency, this term is function of the cutoff ratio, RC, and the function of the compression ratio, which is R. If I take place this RC, take this relation, and substitute RC as function of Q added and divided by V1 V1 and the function of the compression ratio R, then we can get a relation of thermal efficiency only as function of what? Q added. We have excluded the term RC from this relation. It will be function of Q added V1 V1 and also function of the compression ratio. We have excluded the term of RC. Now we can just plot the relation between eta thermal, which is dimensionless parameter, and this parameter Q added over V1 V1 as function of what? As function of the compression ratio. And here is the figure. Here is the top figure. If we took this relation for eta thermal, we got this relation RC as function of this term Qn divided by V1 V1 and as function also of the compression ratio R. take this equation and substitute it here, then we can get the thermal efficiency as function of the compression ratio R, and we can replace this RC by this relation. It will be function of R plus Qn divided by B1 V1. Then plot this relation, that will be the figure. As you can see here, Shabab, let's say at this term Q over B1 V1 is equal to 40. As we increase the compression ratio, the efficiency should be increased. Okay? But what will happen if we reduce the heat added, Q divided by B1 V1? If we reduce it to 20, that means in this case, when we reduce the heat added, in this case, the efficiency will be increased. That's the same compression ratio. But if we make it minimum 0, heat added is equal to 0. That means, Shabab, we have added all heat at point number 2, at constant volume. That means in this case, the efficiency of the diesel engine will approach the efficiency of the Otto cycle, which is the efficiency of gasoline engine. And the efficiency should be maximum in this case. So at the same compression ratio, Shabab, the maximum efficiency of a diesel engine is to approach the efficiency of the Otto cycle. And in this case, we can say the value of the RC cutoff ratio will equal to 1 in this case. So at the maximum efficiency for a diesel engine, the value of the cutoff ratio, which is V3 divided by V2. If we added all heat at 2, that means 0.2 is the same as 0.3. That means the cutoff ratio should equal to 1 in this case. Okay, is it clear, Shabab? Yani, it's a kind of proofing, but you can go through. Also, we can prove a relation also for the indicate mean effective pressure. Indicate mean effective pressure is an important parameter, Shabab, to compare the network out. Indicate mean effective pressure is defined as the network out divided by the difference in volume, which is the displacement volume. Displacement volume, which is V1 minus V2. Okay? So it compares the power output of different engine having different displacement volume. Okay? We may have a small displacement volume, but it can produce higher power. That means it should have higher indicated mean effective pressure. So as the indicated mean effective pressure increase, that means actually this engine is more powerful in this case. So if you are going to get a car, a new car, and you are comparing different cars, you should not compare the colors and all of that stuff, Shabab. You have to compare actually analytically here, which one can actually be more efficient in this case. You are a mechanical engineer, okay? Or an engineer in general. So in this case, we have to look at those specific parameters. If we have higher indicate mean effective pressure, that means this engine is more powerful. But it does not mean, Shabab, that this engine, if it is more powerful, that it is actually more efficient. Okay? We have to look at actually some other terms. So let's look here. Work net divided by V1 over V2. Work net, which is eta thermal by Q added, divided by V1 minus V2. If I took V1 as common, so it will be 1 minus V2 over V1, which is 1 over R. So that should equal to eta thermal multiplied by Q added divided by V1. That should be the indicate mean effective pressure. Multiplied by R divided by R minus 1. Okay? So if we divided both sides, this is a pressure, Shabab. It is not real pressure, but its unit is pressure. We call it indicate mean effective pressure. If I divide it by B1 to make this term dimensionless, divide by B1 here, so Q added divided by B1, this term also will be dimensionless. And this is dimensionless parameter, which is eta thermal. R is the compression ratio, is a dimensionless parameter. Now we can take this relation and plot the relation between this term, indicate mean effective pressure over B1, and this term as function of what, Shabab? Compression ratio. And then look at this. So you can see here, Shabab, this is the second figure, not here. As we increase the amount of heat added over B1 V1, that means in this case the indicate mean effective pressure over B1 will be increased in this case. At the same compression ratio, when we increase the heat added, the indicate mean effective pressure will be increased. But as you can see here, Shabab, that does not mean that the system in this case, when we add more heat, will be more efficient. No. In case of diesel engine at the same compression ratio, when I add more heat, the efficiency will get down. Okay? So that does not mean, if we have higher indicate mean effective pressure engine, that it is powerful. That's okay. It is powerful. It will give more power. But in this case, the efficiency will be less in this case. As you can see, the indicate mean effective pressure will be increasing by adding more heat at the same compression ratio. But at the same compression ratio, when I increase the heat, that means I'm moving down. So the thermal efficiency will be reduced in this case. Is it clear, Shabab? Is it clear?
Yes, Doctor.
Abdul Mohsen, is it clear?
Yes, Doctor.
طيب شباب, let's solve an example. يعني it's very systematic. I will يعني the proof, I will not ask you for the proof in the exam, and in the exam I will give you the relation. يعني I will not give you the isentropic relation B2 over B1, or you have to get this relation, but I will give you at the end the definition of the thermal efficiency for a diesel engine or gasoline engine or whatever. I will give you the expression and then you can solve. But يعني you have to, it's very systematic. I have to remember anyway, Shabab, the representation of the cycle on the PV diagram. And also we can represent this cycle, Shabab, on the TS diagram. It will be very similar. From 1 to 2 is the isentropic compression. 2 to 3 is the constant pressure heat addition. And this is the isentropic compression. From 3 to 4, isentropic means, Shabab, it should be vertical line on the TS diagram. Isentropic means the S is constant. So from 3 to 4, this is the expansion work, isentropic expansion, and from 4 to 1, this is the heat rejection in this case under constant volume. Okay, and we see the area contained by the curves of a cycle on the PV diagram. That area represents the network, and in case of TS diagram, the area contained by the cycle processes is equal to the net heat transfer. Okay, and for a cycle, we said Q net is the same as work. The net heat transfer is the same as net heat add for any system working on a cycle. But let's look at this example, Shabab. This is an explanatory example. So we said we have a diesel engine. The compression and the pressure at the air standard diesel cycle operating with the compression ratio of 18. So that means we have R is equal to 18, which is the compression ratio. And we have here actually the condition at the beginning of the compression stroke. That means at point 1. This is the beginning of the compression stroke, when the piston is at the bottom dead center. So B1 is equal to 0.1 megapascal, which is 100 kilopascal. Please convert the unit. I think you are aware of all of that, this stuff. So convert it from megapascal to kilopascal. We have the temperature T1 is equal to 300 Kelvin. And he is giving also the value of the cutoff ratio, RC, is equal to 2. So V3 over V2 is equal to 2. And this is air standard cycle. He just gives the properties of air. Those properties we can get from table A1, should have access to for air. And I think those value already. And we need to calculate the pressure and temperature at all points. Calculate also the network of the cycle and calculate the indicate mean effective pressure. So I will go process by process. So from 1 to 2, we have this process. We have this process is the compression process, isentropic compression. So delta S is 0. We can apply the isentropic relation. T2 over T1 will equal to B2 over V1 to the power K minus 1 over K is the same as V1 over V2 to the power K minus 1. V1 over V2, which is R. V1 over V2, which is R to the power K minus 1. And the R is the compression ratio is given equal to 18. K for air is equal to 1.4. And we have the pressure B1 is equal to 100 kilopascal. Temperature T1 is equal to 300. So based on this relation, I can calculate T2 and I can calculate V2. So here you can see the value of T2. The calculated value here is equal to 953 Kelvin, and the value of V2 is equal to 5,720 kilopascal. Okay, so those are B2 and T2. Type process from 2 to 3. From 2 to 3, we have pressure. B3 is the same as B2. So B3 is the same as B2. So B3 is the same as B2, which is 5,720 kilopascal. And we have T3 over T2. From the ideal relation, we have proved that should equal to B3. Sorry, V3. That is V3 divided by V2. This is constant pressure process. We can say B2 V2 divided by T2 is the same as B3 V3 divided by T3. We have the same pressure, so we'll result with this relation. V3 over V2, which is the cutoff ratio, which is given, is equal to 2. And we have T2, we have just calculated. Then we can calculate the temperature T3. Temperature T3 is 1907 Kelvin. We call this temperature at 0.3 is the maximum temperature of the cycle, the limiting temperature of the cycle. If I asked you to calculate this temperature, I asked you to calculate the maximum temperature of the cycle. That means I need the temperature at point T3, which is the temperature after the combustion process. And that should give us a theoretical indication about the temperature inside the cylinder for the diesel engine. It should be theoretically around this value. Yani due to the heat transfer to the cooling system, because we assume here in this cycle we don't have heat losses, but due to the heat losses, the temperature should be a little bit less than this value. But this is a theoretical indication about the temperature inside a diesel engine. By process from 3 to 4, we have T4. Let's say T4 over T3. This is isentropic expansion will equal to B4 over B3 to the power K minus 1 over K, which will equal to V3 over V4 to the power K minus 1. Type V3 over V4, if we divide it by V2 in both sides, up and down, that should equal to R, RC divided by R to the power K minus 1. We have RC. We have proved this relation. RC is equal to 2, and R is equal to 18. K is equal to 1.4 again. We have V3 is the same as B2. We have calculated. And we have T3. We just calculated this value. So based on the isentropic relation, I can calculate T4 and the B4 in this case. And by this, we have calculated all the pressure and temperature through the whole cycle from process 1 to 4. But we need to calculate the thermal efficiency. So it's a direct substitution. So the thermal efficiency we should equal to eta thermal will equal to work net divided by Q added, which will equal to 1 minus Q rejected divided by Q added. Q rejected, the rejected heat from 4 to 1 is equal to CV multiplied by T4 minus T1. CV for air. CV shabab, here in this problem I give you CB and I give you K and I give you R. Can I get CV? We have CV is equal to CV plus water plus the gas constant R. I give you R and I give you CV, then you can get CV. If you calculate this, it will be about 0.716 kilojoule per kilogram Kelvin. This temperature, either you can substitute by degree C or Kelvin. We have T1 and T4. Then this heat will be the specific heat. We can calculate this value in kilojoule per kilogram. You can check those values, try to practice it and calculate this value and check it. This is Q rejected, and we said Q added from 3 to 2. 2 to 3 will equal to CV multiplied by T3 minus T2. And CV is equal to 1.0 something, 1.005. And we have T3, T2, then we can calculate Q added in this case. We have Q added, Q rejected, then we can calculate the thermal efficiency. If you calculate the thermal efficiency, this value will be about 0.6. So this value, if you calculate it, will equal to 0.6. or we can multiply by 100, so the efficiency will equal to 63% in this case. But we need to calculate the work net. Work net for a cycle is the same as Q net, which is Q added minus Q rejected. We have calculated Q added and the Q rejected. If you calculate this difference, it will equal to 605 kilojoule per kilogram. Okay? And we need to calculate also the indicate mean effective pressure. The indicate mean effective pressure, which will equal to work net divided by the displacement volume. So the indicated mean effective pressure is the net work divided by the displacement volume, which is V1 minus V2. As I told you, this is a closed system. So we can consider the specific work divided by the specific volume, V1 minus V2. If I divide it by mass up and down, so this volume will be specific volume, this work will be specific work. We have calculated per unit mass, the specific work. So that means this is specific volume V1 minus V2. So if we took it, that will equal to work net divided by V1 will be V2, 1 minus V2 over V1. So it will equal to R minus 1, and here we have R. Okay. R is equal to 18. This value is given. We have calculated work net. But how we can get V1 issue? How we can get V1? Specific volume V1. We can apply the ideal gas equation. At any point it is applied. We are considering the ideal gas model. BV, B multiplied by total volume is equal to MRT. But if I divide it by mass, it will be specific volume. So V1, specific volume in meter cube per kilogram. We can calculate it. We have R 0.287. The temperature T1 is 300. The pressure V1 is 100 kilopascal. Then I can calculate V1 in meter cube per kilogram. Just substitute here. Then I can calculate the indicated mean effective pressure. This is in kilojoule per kilogram. That means the indicated mean effective pressure will be in kilopascal in this case. Okay, is that clear, Shabab?